7.1 Construction of a composite video signal. Figure 7.1 Composite video signal formation. In Figure 7.1, three forms of composite video signals are shown, which are camera signals, with the addition of blanking pulses and alignment pulses. A. Camera signal for one horizontal line. B. An H horizontal discharge pulse is added to the camera signal. C. H alignment pulse, horizontal, added to the discharge pulse. In Figure 7.2, successive voltage and current amplitude values are shown for viewing two horizontal lines in the image. As time increases in the horizontal direction, the amplitude changes for white, gray, or black colors in the image. Starting from the leftmost one at time 0, the signal is at white level and the scanning beam is to the left of the image. Once the first line is displayed from left to right, a variety of camera signals with various amplitudes are obtained that correspond to the required image information. After horizontal tracking produces the desired camera signal for one line, the tracking beam is to the right of the image. Then a blanking pulse is inserted to restore the amplitude of the video signal up to black level so that the repeat trace can be cleared. Figure 7.2. Composite video signal for two horizontal lines. Once the discharge time is long enough to cover trace repetitions, the discharge voltage is removed. Then the payment file is on the left, ready to pay the next line. In this way, each horizontal line is paid successively. Note that the second line shows dark image information near the black level. With regard to time, the signal amplitudes right after blanking in Figure 7.2 show information corresponding to the left side at the start of the display line. Just before discharge, the signal variation corresponds to the right side. The exact information in the middle of the display line is the half time between discharge pulses. Alignment polarity in composite video signals. Video signals can have two polarities: 1. Positive alignment polarity with alignment pulses facing upwards as in Figure 7.2. 2. Negative alignment polarity with the alignment pulses facing downwards as in Figure 7.3. The video signals shown in Figures 7.2 and 7.3 both contain the same image information. Video with negative alignment polarity is required on the control grid of the picture tube to reproduce the image. Then the discharge level is negative to add beam current for black. Video with positive alignment polarity is required at the picture tube cathode. In addition, negative alignment polarity is the standard for internal or external signals from video equipment such as television cameras, video control equipment and distribution networks. The standard amplitude is 1 VPP with negative sync. Figure 7.3, same video signal as in Figure 7.2 but with negative alignment polarity. For either polarity, remember that the white part of the video signal is opposite to that of the alignment pulses. The discharge level should be black. The alignment amplitudes can be said to be blacker than black. Emptying, blanking. The composite video signal contains blanking pulses to make trace repetition lines invisible, namely by changing the signal amplitude to black when the display sequences produce trace repetitions. All image information is turned off, cut off during blanking time. Normally, repeat traces will occur during the blanking time. As shown in Figure 7.4, there are horizontal and vertical discharge pulses in the composite video signal. Horizontal blanking pulses are included to clear the trace repetitions from right to left within each horizontal scanning line. Thus, the repetition rate of horizontal discharge pulses is a line scanning frequency of 15,750 Hz. The vertical blanking pulses clear the scanning lines that are produced when the electron beam repeats tracking vertically from base to top in each field. So the frequency of vertical discharge pulses is 60 Hz for each field. Each discharge pulse turns the video signal black during the discharge time. Figure 7.4. H and V blanking pulses in a video signal. Alignment pulses are not shown. 7.2 IR scale of video signal amplitude on an oscilloscope monitor. The amplitude of the video signal is usually checked along with negative alignment polarity to conform to the IR scale shown in Figure 7.5. IR is an abbreviation for Institute of Radio Engineers, which is now called IEEE, Institute of Electrical and Electronic Engineers. The total IR scale includes 140 units with 100 increasing and 40 decreasing from 0. The peak-to-peak composite video signal includes 140 IR units. Alignment pulse amplitude of the 140 IR units, 40, or close to 29%, are for synchronization. All alignment pulses have the same amplitude, namely 29% of the video signal peak-to-peak. Figure 7.5. Oscilloscope image of two composite video signal lines with IR amplitude scale. Note the 140 unit IR scale on the left. Black setup. Note that the black peaks of the camera signal variation are deviations from the black blanking level of 7.5 IR units, which is approximately 5% of the total. The goal is to ensure that additional carrier signals, subcarrier signals, for colors near black in the camera signal do not interfere with the alignment amplitude. Camera signal amplitude white peak ACK is approximately close to 100 IR units. However, the black setting is 7.5 units to offset the black in the blank level image. By subtracting the black fitting from the peak white, the result is 100 minus 7.5 equals 92.5 IR units for camera signal variation. This number is 66% of the total 140 IR units. Horizontal discharge time. Details of the horizontal discharge period are depicted in Figure 7.6. The interval mark h is the time required to trace one line, including tracking and repeating the trace. Thus, the time for h is 1/15,750th of a second or 63.5 microseconds. The horizontal discharge pulse width is only 0.14 h to 0.18 h. Take an average of 16% as a typical value. So the horizontal emptying time is 0.16 by 63.5 microseconds equals 10.2 microseconds, approximate. Now, we subtract this value from the time h, which is 63.5 microseconds. 63.5 microseconds 10.2 microseconds equals 53.3 microseconds, so 53.3 microseconds is the time required for visible viewing, without blanking in each horizontal line. To clear h, a horizontal trace is required. Superimposed on top of the h blanking pulses are the narrower h alignment pulses. As shown in Figure 7.6, each alignment pulse h is 0.08 h, or half the average width of the blanking pulse. So this alignment time is approximately 10 microseconds divided by 2 or 5 microseconds. Front and back porches, front porch and back porch. During the remaining half of the discharge time, which is also 5 microseconds, the signal is at the discharge level. The part immediately before the alignment pulse is called the front porch, and the back porch follows the alignment pulse. The width of the front porch is 0.06 h. This time period is 1.27 microseconds for the front porch and 3.81 microseconds for the back porch. Note that the back porch is 3 times longer than the front porch. All time periods within a horizontal line are summarized in Table 7.1, with the necessary tolerances. Figure 7.6. Details of horizontal discharge and alignment pulses. Time h is 1/15,750th microseconds equals 63.5 microseconds. In the image below the signal, the black edges show discharging. B. Blanking h moves into the image to show the effect on the screen. Brighter than normal. H clearing and H paying. The blanking time is slightly longer than the typical value of trace repetition time. As a result, a small portion of the trace is usually cleared at the start and end of each payout line. This horizontal emptying effect is depicted by the black bars on the left and right of the image in Figure 7.6a. The black on the right edges corresponds to the front porch of the horizontal emptying, before the trace repetition begins. Generally, the horizontal trace repetition starts at the first edge, leading edge, of the alignment pulse. Just before repeating the trace, when the scanning beam completes its tracing to the right, the blanking level of the front porch will cause the right edge to turn black, with a small amount of each line blank out in this way. This black bar to the right can be thought of as a reproduction of the front porch portion of the horizontal blank. See Table 7.1. Horizontal discharging details time period in microseconds. Total line h 63.5, h discharge 9.5 to 11.5, alignment pulse h 4.75 plus or minus 0.5, front porch 1.27 minimum, rear porch 3.81 minimum, visible line time 52 to 54. After the anterior foyer of emptying, horizontal trace repetition can begin when the alignment pulse is initiated. The flyback must be blank because the alignment level is blacker than black. Although trace repetition generally begins with an alignment pulse, the amount of time required to complete the flyback depends on the scanning sequences. Typical flyback time is 7 microseconds. The emptying time after the front porch is 8.93 microseconds, which is calculated as 10.2 minus 1.27 equals 8.93 microseconds. Now reduce the flyback time by 7 microseconds. 8.93 minus 7.00 equals 2.93 microseconds. 2.93 microseconds is the emptying time, which is still the highest after the repeat trace to the left periphery has been completed. Even though the discharge is still in progress, the sawtooth deflection waveform causes the charge beam to begin tracking along the flyback. As a result, the first part of the trace on the left is left blank. After 2.93 microseconds of empty tracking time in the left periphery, the blanking pulse was removed. The video signal thus reproduces the image information as the payment beam continues its tracking for 53.3 microseconds of involved tracking time. However, a small amount of each line that is cleared at the start of tracing forms a black bar at the left edge of the raster. This black border on the left is part of each rear porch following the horizontal alignment. Blanking bars on the sides have no effect on the image other than reducing its width slightly compared to the blank raster. However, the horizontal viewing amplitude can be increased to provide the desired image width. Figure 7.6b shows the effect on the picture tube screens for the front and rear porches during blanking H. The brightness was set higher than normal, to make the blank brighter than black. Also, the payment to emptying phase must be shifted to include the emptying time into the tracking time. H discharge time summary for typical values. The width of each discharge pulse H is 10 microseconds. The alignment pulse width H is 5 microseconds or half the discharge time. Just before H alignment, the front porch is 1.27 microsec. The black hole just after the H alignment is 3.81 microseconds. Note that 1.27 plus 3.81 is approximately 5 microseconds. Propagating this to 5 microseconds for H alignment will give an H discharge time of 10 microseconds. Vertical discharge time. Vertical blanking pulses change the amplitude of the video signal to black so that the traces blank out during repetition of the vertical trace. H lines emptied by emptying VA time of 1333 is long enough to cover many complete horizontal payment lines. If we divide the vertical blanking time of 1333 by 63.5 total line periods, we get 21. So 21 lines are left blank in each field, or 42 lines in the frame. The total number of blank lines in the framework can also be calculated as 0.08 times 525 equals 42. A relatively long time empties not only the vertical retrace lines, but also a small portion of vertical tracking at the base and peak. Pulse in discharge time v. The alignment pulses inserted in the composite video signal during a wide vertical blanking pulse are shown in figure 7.7. These include equalization pulses, vertical alignment pulses, and some horizontal alignment pulses. The signals are displayed at intervals between the end of one field and the next. To illustrate what happens during the vertical emptying time, the two signals displayed one above the other are the same, except for the half-line shift between successive fields necessary for the display of intertwined odd lines. Starting at the left in figure 7.7, the last 4 horizontal viewing lines on the raster base are shown along with the required horizontal alignment and blanking pulses. Immediately after following the last variable day, the video signal is made black by a vertical blanking pulse in preparation for repetition of the vertical trace. The vertical blanking period begins with a group of 6 pulses, spaced at half-line intervals. Next is a jagged vertical alignment pulse that actually produces a vertical flyback in the scanning circuit. Serrations also occur at half-line intervals. Thus, a complete vertical alignment pulse is 3 lines wide. Following the vertical alignment is another group consisting of 6 equalization pulses and a series of horizontal pulses. During the entire vertical blanking period, no image information is generated, because the signal level is black or blacker than black so that the repetition of the vertical trace can be blanked. The details of all these pulses in the vertical discharge interval are summarized in Table 7.2. Note the position of the first equalizing pulse at the start of vertical discharge in figure 7.7. In the signal at the top, the first pulse is a full line beyond the previous horizontal alignment pulse in the signal below. For the next field, the first pulse is half a line away. This half-line time difference between the even and odd fields continues through all subsequent pulses, so that vertical alignment pulses for successive fields are timed for intertwining odd lines. V clearing and V paying a jagged vertical alignment pulse forcing the vertical deflection circuit to initiate flyback generally will not start with the start of vertical alignment because the alignment pulse must build charge in a capacitor to drive the alignment circuits. If we assume that the vertical flyback begins with the leading edge of the third cleat, then the time of one line elapses during vertical alignment before the flyback begins. Also 6 pulses to equalize the same 3 lines occur before vertical alignment. So 3 plus 1 equals 4 lines are left blank at the bottom of the image, just before the repetition of the vertical trace begins. How much time it takes for the flyback depends on the viewing sequence, but a typical vertical trace repetition time is 5 lines. Once the scanning file trace is repeated from the bottom to the top of the raster, 5 complete horizontal lines are produced. This vertical trace repetition can be completed easily during the vertical emptying time, with 4 lines emptied at the base before flyback and 5 lines emptied during flyback. 12 lines remain out of a total of 21 during vertical blanking. These 12 blank lines are at the top of the raster on the downward vertical tracking surface. In summary, 4 lines are cleared at the base and 12 lines at the top in each field. In the total framework of the two terrains, 8 lines are cleared at the base and 24 lines at the top. The viewing lines produced during vertical tracing, but which are made black by vertical blanking, form black bars at the top and bottom of the image. The image height decreases slightly with blanking, compared to an unblanketed raster. However, the height can be easily improved by increasing the amplitude of the sawtooth waveform for vertical masking. V discharge time summary. Repeated vertical blanking pulses at 60 Hz are inserted for each vertical viewing field to blank the repetition trace V. The discharging pulse width V is 1333, sufficient time for the complete visualization of 21 horizontal lines in each field. The serrated V alignment pulse is also repeated at 60 Hz to align the vertical sidings in each field. The width of each V alignment pulse is 6 half lines or 3 complete H lines. The V alignment pulses are made much larger than the H alignment pulses so that they can be separated in the alignment circuits on the receiving aircraft. Each of the V alignment pulses has teeth at half-line intervals to maintain horizontal alignment continuity during the V alignment time. Just before and after each V alignment pulse there is a group of 6 equalization pulses. Due to the half-line spacing of the equalizing pulses, the length of each group is 3 H lines. Half-line spacing will maintain continuity of horizontal alignment with alternating equalization pulses during the vertical discharge time. With 2 pulses in time from a complete H line, the equalizing pulses will be repeated at a rate of 2 times 15,750 equals 31,500 Hz. Groups of equalizing pulses just before and after V alignment are used to improve vertical alignment in even and odd fields. The half-line serrations in the vertical alignment pulse also have a frequency of 31,500 Hz. In fact, the pulses for equalization and vertical gearing are similar pulses but with opposite polarities.